So my name is Royale. I am the group reporter for Group 1, included with Mr. Logan Campbell and Riley Craig. So going into what we're going to talk about today is, of course, thermocouple time constant. So first I'm going to ask the question is basically what is the goal of this experiment? So as we see, the goal is basically to determine the thermocouple time constant using a first order response system. And they kind of understand, okay, what is the thermal time constant? Or basically, what does that mean essentially? So actually, essentially represents the time needed for the system to change, 63.2% of the total temperature change. So in other words, kind of making it simpler, a smaller time constant basically relates to a faster response to the sensor, though a larger time constant means actually it's a slower sensor response time. So kind of going into some theory and background, understanding basically what we're working with, the lump capacitance and energy balance, and we all love this topic and concept from heat transfer as well as a little bit of thermal as well. So essentially we see here on the left-hand side, we have the initial equation before the integration, and once we integrate that equation, we can now get temperature basically as a function of time. So you see here all the components. So we have the factor in density as well, which is the density of the thermocouple, as well as the volume of the thermocouple, so the heat of the thermocouple, along with the convection heat transfer coefficient, as well as the surface area of the thermocouple. So basically that size of the actual sensor, it plays a big part in the readings and the results we're getting in. Going on to more theory. So after we basically do some more math and basically get a simplified version for the thermocouple time constant equation, and then now we can find a temperature equation, a time equation to get time as a function of temperature. So kind of going back into the lump capacitance method, basically what we assume, that the internal temperature in the object is uniform at any point in time. So essentially temperature is a function only of time, not a point or like location on the object. As well as the method basically uses a small Boyle number, so less than 0.1, as well as using a first order relationship. Going to some results. So it's basically looking at first the insertion, it was actually inserting the thermocouple into like the water bath during the experiment. So we see here is basically just the raw temperature versus time, and basically it shows that first the response is not instantaneous, like the temperature doesn't just shoot up immediately. As you can see, it's like a long period where temperature really change. But then we can actually see that later on it's actually a sharp increase. So the response is actually a function of temperature after the insertion or the removal of the actual thermocouple sensor. And we see actually identifies when the time temperature changes occurs, and you see that sharp increase right between like that 10 and 20 second period. As well as you can also understand that this depicts essentially a first order behavior as we look at the system here. Going to more plots, so looking at basically the normalized versus time. So now here we actually see the dimension is basically temperature response, and it reveals the basically expected exponential decay. Ignore my graphs here, look kind of crazy over here, but essentially this decay shows what happens after we plunge that thermocouple into that water for the insertion. And on the right hand side, the local, the law of normalized temperature versus time. And it indicates that basically time is actually equal to the thermal time constant, and it gives us a nice visual of the time constant as well. So now going on to the removal process. So it actually shows a similar pattern to the insertion, however it's reversed. So essentially we see as we remove the thermocouple from the bath, it's reversed because heat is now being removed from the system. Going on to our normalized and our log temperature versus time. So we see here that the report results here as well. So I'm going to go over to our kind of summary of our results. It's kind of looking at an overall viewpoint. Basically, you have the segment here between the insertion and removal, as well as the starting point. So it's like the point of I basically put into Excel. My start was basically the point in which it started, so you see the response, as well as the end point where the response has to slow down. Temperature, the outside temperature was the slope, intercept, and then the time constant, something I want to kind of focus on because it was actually interesting results that I found when I looked into it, because I felt like it was kind of weird, kind of wrong, honestly. So one thing that I noticed, I think it was not the ideal situation, was actually my insertion value was larger than my removal value. So typically it should be the other way around, as I looked in. So this could be a result of a few things. First, human error. I'm not the best with Excel. So that could be one factor, as well as number two, it could be, if looking to it, if you have a large sensor delay due to like such a drastic, certain change, because it goes from being an outside temperature to now you're plunging it into a hot water bath. So that could just like cause the sensor to like kind of like freeze up a little bit before it starts to react. And it also could be a result of the removal. When you took it out of the bath, that is the cooling in the air actually basically occurred much faster than expected because the evaporation of water causes it to cool a lot faster. So therefore, the removal value is actually smaller, representing a faster response time. Kind of going through some topics, basically as I looked into this more, I was like, okay, how can we manipulate the time constant? Can we see that it changes based on the environment? So first, increasing the mass of the system increases the time constant, of course. More mass, bigger bodies, it takes longer for it to get to that desired state. As well as using material with, of course, a high thermal conductivity increases the response time. And the small sensors actually result in a faster response time than larger ones. So I think in our lab we actually really a small sensor on thermocouple, so that should result in like basically quicker response times in our sensor and our time and our temperature change. In conclusion, looking at basically kind of what we all seen throughout the lab and actually do this presentation, which y'all continue to see, and the next presentation is coming up, is basically the behavior of a first order system. And also we see the time constant changes, and it's basically driven by convection conditions, as well as the third point is that we actually experimentally manipulate and also affect the time constant that we're looking to get. Secure my references. Thank you very much.
Can you give a round of applause? Does anybody have any questions for Ryan?
Can you explain how smaller sensors respond faster?
Yeah, so from when I was looking into it, it's the fact that it basically has a quicker reaction. So think about the large sensor.
Can you open the equation please?